Hello and welcome back. The Squeeze Theorem is a useful little theorem that can help you evaluate certain kinds of limits that otherwise are difficult to evaluate. So here's what the Squeeze Theorem says. It says, suppose you have a function that's trapped between two other functions. So this function g is trapped between the functions f and h. H is on top, f is on bottom, and g is in the middle. So we can look at the picture off to the right, seeing that h here is just some example function that's on top, f is some function that's on the bottom, and g is some function that's in between. So what the Squeeze Theorem says is that if this is the case, if this is your setup, and if the limit as x approaches a of f, the bottom function, is equal to the limit as x approaches a of h, so they're both equal to this limit L. L would be whatever the y value is, so it would be like over here somewhere. This is what L would be. Then the limit as x approaches a of g of x, that function that's in between, has to also equal L. So in other words, if f and h are both going to L, then g has to go to L as well. Now this is called the Squeeze Theorem because you can see that this g function is being squeezed into this limit L by f and h. Because the whole thing is that if h has to always be above g and f has to be below g, and so these two are squeezing g into a tighter and tighter space, and so g has to be going to L if both h and f are going to L. The Squeeze Theorem has some other names like the Sandwich Theorem, because h and f are like the bread, and then g is like the stuff in between, maybe like a veggie burger or something like that. Or the Pinching Theorem, because there's this like pinching thing going on. Or my favorite name for the theorem is the two policemen and a drunk theorem, where h and f are like the two policemen that are escorting this drunk to the police station, who's kind of bouncing back and forth between the policemen. So g would be the drunk. But whatever you want to call it, we're going to mostly just call it the Squeeze Theorem because that's kind of the standard. This is, again, a useful little theorem if you can find functions that bound your function that you're interested in on top and bottom. If it can bound it, then it can help you out. All right, so here in example 13, we're asked to use the Squeeze Theorem to prove that the limit as x approaches 0 of x squared times sine 1 over x is equal to 0. And it's worth it to note that you can't really just plug in x equals 0 because you're going to get a division by 0 inside the sign. You'll have a 1 over 0, which is undefined. And so there's an issue going on there. In fact, there are other things going on. If you approach 0 from the left or the right, you get different kinds of infinities going on with 1 over x. And not only that, but even if you just approached from the right, you'd have 1 over 0 approaching from the positive side. That would be going to infinity. And if you think about what happens to the y values of sine as you go to infinity, it just oscillates back and forth and back and forth. It never really settles in on any particular y value. It bounces back and forth between -1 and 1. So sine 1 over x is particularly bothersome when it comes to limits because it can have that effect of oscillating forever and never really settling down on any particular number. A very antsy function. But what we can do to tame this particular function is trap it between two other functions that are both going to the same thing as x approaches 0. And the way you can think about setting this up is first starting with noting that sine 1 over x itself is trapped. It's trapped between two values. What are the two outputs that sine is trapped between? If you said -1 and 1, that would be correct. Think about the regular sine function. The regular sine function is trapped between, between -1 and +1 for its outputs. This is just like sine x, regular sine x. So the outputs of sine, no matter what the inputs are, the outputs are going to be trapped between -1 and 1. So it doesn't matter what the inputs are, the outputs of sine are trapped between -1 and 1. The same thing would be true of cosine. Now if we took that three-part inequality and multiplied it through by x squared, so multiply So you're multiplying all three parts of this inequality by x squared, just like multiplying them by a number like 2. You know, you could multiply all three parts by 2. So if you multiply through by x squared, then what you're going to get is negative x squared on the left, x squared sine 1 over x inside, which is the function that we're interested in, and then x squared on the right. So now we've got the function that we're interested in trapped between these two other functions, negative x squared and positive x squared. So this is great. Now we've got this function that we're interested in squeezed between these two other functions. So tying it into the function names that we gave in the squeeze theorem, the lower function would be like f, the middle function is g, and then x squared is h. So now what we have to do is check to see what is the limit as x approaches 0 of the upper and the lower functions, so the h of x and the f of x. So let's look at the limits as x approaches 0 of each of those. If they're equal to the same thing, then our middle function has to approach the same thing. So what is it that these two outer functions are approaching as x approaches 0? If you said 0, that would be correct. You just plug in x equals 0 into these, and that's what you end up getting. And I don't know why I put the parenthesis right here. There, that looks a little better. So now the squeeze theorem is going to kick in. And say that the middle function, the x squared sine 1 over x function, must also go to 0. This is kind of proofish, so I'm going to put a little box. Remember that this box is like a way of celebrating at the end of a proof. After all, it did say to prove that this limit was equal to 0. By the way, I didn't really mention it, but notice that it told us what the limit was equal to. So here, pretty clearly, the goal is not going to be to figure out what this limit is equal to. It's going to be to show why this is true. And the squeeze theorem is a great way to show why this is true, why this limit is equal to 0. One last thing I wanted to mention is here from the picture, we can see that this limit is actually 0 as well. So notice that here are the oscillations of sine that are getting faster and faster as we get closer to 0. Same thing in the other direction. But the y values are being pushed down to a y value of 0. They're being pushed down by this x squared factor that's in front. And if you graphed the top and the bottom function, the x squared and the negative x squared, you would get these parabolas opening up and down. That meet right at the top of each of these oscillations. Because wherever sine 1 over x is equal to 1, then the function is going to have the same y value as x squared. So wherever sine 1 over x is 1, the 1 times x squared will just be whatever the y value of x squared is. So they're going to meet right there up at the top of each of these oscillations. So this is like the x squared function. And then on the bottom, you're going to have the negative x squared function. Can't really draw this very well. There we go. So this is negative x squared. So this is like an envelope with a little x squared sine 1 over x letter inside, if you will. You can really see that squeezing happening right there between the x squared and the negative x squared functions. So that's it for the squeeze theorem. Thanks for watching this part, and I'll see you in the next part.